Now I promise this is really the last presentation for the first week. I know it has been already by far too much, but I'm coming now to the conditional probability. Usually we know that something is happening or definitely will happen, and we want to see the probability of other things happening at the same time. So we need to think about how to compute the probability under the assumption that something holds true, something did happen. And this is again very easy, right? So simply you know that the sum of two of the dice you throw together is, I don't know, 9, and you ask what's the probability that something occurs there. So a 5 or whatever, right? Or a 6. How to view this? So simply, again, the intuition is very easy. If you go to the classical probability, so just counting the points, so what does it mean? So it means if you know that something happened, then you know that you are in a subset. So it means that you simply shrink the total space of the original sample space to the hypothesis, to the assumption H. And then, of course, your events will have to be shrink to that subspace as well. So you consider the intersection. And that's a very nice thing, right? So you easily can play with that. Well, and in the introductory chapter as the warm-up, I didn't touch much of the conditional probability, but it comes back in the book in the chapter devoted to probability and statistics. And this will not be in my first 5 courses at all. That will be coming later, but we shall come sooner or later always back to these ideas. And so now let's have a jump. And you see, I have jumped to page 917 in the current version of the textbook. And there is conditional probability again. And you see the same formula as we had already in the page before. And there are some properties and things related to that in more detail. And in particular, what we can see immediately is what we call the so-called law of total probability. So if you want to compute the probability of A under the condition B, then you can split the condition B into finite number of mutually distinct exclusive events, and you simply write it as a sum of the individual possibilities, right? And for each of them you see that the probability of which counts with this part is the probability of A under BI, but multiplied by probability of the BI under the hypothesis of B, right? And these things together give us what we need, and this leads then directly to what is called the Bayes rules. And the Bayes rules are absolutely basics of most of the so-called Bayesian statistics, and in data science I think this is the one which makes more sense, or many people think that it makes more sense than the frequentist one. But don't touch this now, and look better on the Bayes rules. So the probability of the events A and B can be computed this way. So the A appears under the condition of B with the probability which can be computed this way. And this is a very computable thing in many cases, right? And you can also substitute the probability of B with this kind of thing, which is the application of the total probability I mentioned just a second ago. And this is a quite nice thing. And just to have at least one example, in the interactive syllabi you have got this link, which is something we can again get into mouse. And go to the Sage cell. So this is still the one we had there before, so I will just replace it. And let's have a look what we've got here, right? So I want to deal with the problem with the following problems. Imagine you have got some test, and the test is there to test, say, the intelligence of the future students of a university, right? And let's now skip the problem. What does it mean that the student is intelligent? But let's assume we know what's roughly the percentage of the population which satisfies this qualification of ours. And let's imagine that our test is done in such a way that quite many of the really good ones pass it, so say 90 or I don't know how many percent. So that's the probability of good ones. You see, I'm just going from roughly a half to 1 with some step by 5%. And at the same time, there are the bad ones, and there is also the probability that being a not intelligent student or future student, so say applicant, you still pass the test, right? So you can also imagine it's a test of being ill, right? So imagine we are testing someone whether is infected by the HIV or something similar, right? So the virus. And then of course the formula we've been talking about is just this. So it's just to find a probability that under the assumption that someone passed the test, he's really good. So in case of the students, it means you are interested in the fact or in the situation where you meet a student enrolled already to the program who passed, of course, the test then, and the question is whether he's intelligent or not, right? So it depends on our definition, of course, but here it's just formula. With the disease, it's easier. So we find someone who is supposed to be HIV infected, and the question is whether he really is, right? And let's have a look what it does. So again, I have done it this interactive way. So say that we have got the sensitivity of the test such that, I mean, nearly all the really good ones pass, and say 10% of the bad ones pass as well. So it means the test was perhaps too easy. So if it was too easy, maybe it's even more probable that nearly everybody among the good ones does it. But still, you see that if the probability we expect in the population is, say, 10% of the good ones, then such a test would come with a probability 1/2, roughly 1/2 of finding a really good student in our corridor. And that's because the occurrence of the really good ones is assumed to be not very big, and the probability that even the bad ones can pass is relatively high, 10%, right? But imagine what happens if we are doing the same, say, with the HIV virus testing, right? So say we would have a test which is pretty well sensitive. So if you are infected, the test nearly certainly tells it, and the selectivity is pretty good. So let's say that only 5% of the not infected ones will cause a false alarm, right? And then you see that, say, if we expect the reality, so maybe 1 of 10,000 of people will be really infected if you test randomly, right? And then you see that the result is you are somewhere very much in the beginning here. So the probability that someone who was tested positively is really infected is pretty low, so nearly negligible. So therefore, just testing the people is a very serious business, right? So you have to have a sequence of a filter of multiple testing and increase the probability that they are already dealing only with the good ones, right? So with the students, the university, of course, can have good marketing, could already threaten all the bad ones. So the probability, so the distribution of the good and bad going through the trial tests will not be the general frequency in the population, but already something much better. And so I suggest think about this more carefully. And if you look at the code, so you see the formula is pretty easy, and you can just go through that in a straightforward way. So thanks. That was, as I told, much more than enough for the first week. And I hope to get feedback, and I'm looking forward to chat with many of you. Bye.